von Neumann algebras. Von Neumann algebras can be realized in B of H and characterized simply by the identity that, you know, there are self-adjoint subsets which are equal to their bicommutant. So this identity here is the identity of A and the commutant of the commutant. So, you know, we have the classical notation A prime for the commutant. So this is the double commutant. I have this, does everybody have a message that is kind of interfering with the screen? I have a message saying it's recorded. Oh, I see, I should probably, maybe this is only for me, okay. Okay, so I eliminated that, sorry. So for instance, the bidual of a C-star algebra can always be equipped with a star algebra structure so that the canonical inclusion of A into its bidual becomes a star homomorphism. And then, moreover, we have a universal property, which is the canonical property of the bidual here, that for any star homomorphism from A with values in B of H, there is a unique star homomorphism by tilde from the bidual to B of H that extends the original homomorphism pi, and that is normal. And normal in the operator algebra theory means continuous for the weak star topologies of the duals involved. So here the first dual is a double star, which is the dual of the dual, and the other dual is B of H, dual of the trace class. And so we can say that, well, it is continuous, let's say, for the, you know, yes, weak star topology of pointwise convergence on the dual, both on domain and range. That's one way to phrase it. So more generally, a map from a dual to another dual is called normal if it is continuous for, you know, these topologies with the traditional notation for pointwise weak star topology. So in that case, of course, the map is the adjoint of a map. So you have a pre-adjoint, which is usually denoted like that with this U star. Let me check, let me check that things are okay in terms of visual. Does everybody is okay with the second screen? I'm worried about, I have a bar. I don't care because for me it doesn't matter, but is everybody okay with this setting of the two screens?
So some people are finding this to be smaller, so they are requesting it to be one.
Okay. So shall I try then? Shall I try?
Yeah, sure,
okay.
Sure.
Let me see. This might take might be a little bit of a problem, but I might need to stop sharing and do it again. Let's see. I think it's safer if I stop sharing because I don't see. Yeah, here. No, that I think that.
Yeah, this will do. Yeah.
So we're in Zoom, and now I'm on the Zoom menu, and the window. We're on one. Now the question is having the full screen. Old method. I think this is what we want. Okay. Is that good?
Yeah, this is very good.
Okay. Okay. So as I was saying, so you know, I was just recalling the terminology for normal maps, and now a little more background. So if we have a surjective star homomorphism between C-star algebras, then the image is going to be identifiable, of course, with the quotient of the domain by the kernel. The kernel is a closed self-adjoint two-sided ideal, denoted here I. And I'll always say ideals. It will always mean closed self-adjoint two-sided ideal. Okay, this is in the C-star setting. And for any such ideal inside the algebra, the quotient is a C-star algebra. So the important thing for these lifting questions that we will deal with is that every ideal has an approximate unit. Of course, it doesn't have a unit, because if it has a unit, it's the whole algebra, like, you know, any ideal. But there's always an approximate unit, which is a net of a positive operator in the unit ball, which has this property, classical property of approximate units, which you see in the first yellow box. But the more important thing, especially for the lecture today, that will be exploited, very important fact, is that in the C-star algebra context, we can always find a quasi-central idea, approximate unit. So the approximate unit is quasi-central if it has an additional property, which is an approximate commutation that you see in the second box. Okay, so you know the two things are related, but I want to record the two things together. And the important thing, of course, if you are not, you know, if you do not have these things in mind, is that, of course, the first box gives you an approximate unit for I, so it is for any x in I. But the important fact is that the second property, the commutation, is for any x in A. So there is something a little, you know, subtle here. You have to have this commutation with any x of A. And this is the existence of these things. Classical goes back, I think, to, well, probably around work of Arveson, perhaps others before. So basic examples of C-star algebras, of course, as you all know, B of H, n times n matrices, and then the n-dimensional commutative C-star algebra, which is just, which I denote L infinity n, which is just Cn with, you know, pointwise, just obvious pointwise product. There's also a classical example in the algebra, very basic now, called the Kunz algebra. Kunz algebra is the C-star algebra generated by any set of n isometries that satisfy this Kunz relation that you know somehow the space L2 is generated by the ranges of these projections Si, Sj star, the other ones being one. Okay, I'll illustrate things by discrete group questions. So if we have a discrete group, most of the time I'll illustrate this with the free group. Free group will be denoted by Fn or F infinity. And if we have a representation, pi unitary representation of the group, then we have a C-star algebra. So, you know, C-star algebras are really, the theory is really a generalization of group theory. So whenever we have a group, we have a C-star algebra. If we have a group representation, we have a C-star algebra. C-star pi of G is the C-star algebra generated by pi of G, and it's also just the closed linear span of the range of the representation pi. Now, the two special cases are important. One is the universal representation, which is the direct sum, in some sense, of all representations of all unitary representations pi. I'm abusing, I should say, you know, all cyclic representation or something like that to avoid, you know, a too large set. But for the norm, that doesn't really matter. So I'll say it like that, slightly abusive. So that's the C-star algebra generated by the universal representation that contains all representation that contains all unitary representations of G. That's C-star G, simpler notation. And the companion C-star algebra, the reduced C-star algebra, is the one that is generated by the left, we could do the right, but this is tradition is to do things on the left regular representation. So C star lambda G is called the left regular reduced C star algebra of G. Let me start by now setting the stage and defining the lifting problems that I wish to discuss. And immediately, this is what I like, immediately come to questions that are open. So C will be in the whole discussion a C star algebra, and C over I is a quotient C star algebra. And then we have A, another C star algebra. So the global lifting problem is what you think it is. It is very clear. We are going to have, you know, a quotient map. We denote by Q the quotient map from C to C over I. And then the global lifting problem is that we have a map U from A to the quotient, and we want to lift it. So we want to find this map U hat that makes the diagram commute. I'm taking, you know, a broad view for the introduction. You know, soon it'll be made more precise. But I want to distinguish, because that's my main theme, global and local. So local means, you know, local is in the style of Banach space theory. Local theory is the theory when you concentrate on instead of an infinite dimensional space, you concentrate on the collection of all finite dimensional subspaces. So here we look at our lifting problem locally, which means that we consider a finite dimensional subspace E of our A, presumably infinite dimensional, and then we restrict the map U that we are trying to lift. We restrict it to E, so you see the diagram, we get this UE, and our problem is now to get a nice lifting for this restriction to E. So the lifting will be a map like this from E to C, which depends on E. And of course, the lifting problem is, the global problem it has to do with trying to patch these things. If we want to pass from local to global, we need to do some patching. Classical counterexample, let me immediately put this aside, a very famous counterexample of Sobchik that says that if you look at the case of C0 inside L infinity, if you wanted unital, you could take the subspace of convergent sequences instead of the subalgebra of sequences tending to zero. But anyway, in this case, of course, you have here C0, which is an ideal. You have the quotient L infinity over C0, which is a C star algebra. And Sobchik proved that there is no bounded lifting in this situation. Equivalently, and perhaps you know the theorem in this form, there is no bounded linear projection from L infinity to C0. And it's a rather strange fact that actually, if you consider a separable space X in between C0 and L infinity, then there is a projection from X to C0 with norm less than 2, and there is a lifting with norm 1, a global lifting, but only from X over C0 up to X. So this phenomenon explains that even in the simplest case, which is here commutative, we must restrict to the separable case. Otherwise, we have, you know, this immediate counterexample that pops up. Okay, so the lifting, the global lifting question will be mostly on the separable case, although I have a few things to say in the non-separable case. I hope I will not forget. Okay, so now formally, I'll be a little more precise, but I still want to be very general. So just allow me to be a little bit fuzzy on what is script F. So script F is a class of maps, okay? And it's a class of maps between what we need. So between C star algebras, say. And then we say that A has the F lifting property if whenever we have U in F, we can find U hat in F. Just very simple, okay? And then A has the F local lifting property if whenever we have U in F, Well, we can do the things locally. So for any finite dimensional subspace E, then we can find our lifting UE in F. So that, of course, assumes that this script F makes sense, between also the operator space, the subspace E and C. But typical example, and I will now say concentrate on this example, very simple example, contractions. So F is just the class of contractions, meaning maps of norm less or equal to 1 from a Banach space to another. And here we are dealing with C-star algebras, okay? Well, in the case of contractions, the situation is that we have a very famous open problem, and it is open whether simply this is always true. Do you always have a global lifting? Restricting to the separable case. I've already insisted we need to restrict to the separable case. Okay, so this is, I call it open problem 1 in my lectures, because I'll come to open problem 2. This is very old. It goes back to the early 1970s. There was a group of people involved, Ando, T.B. Anderson, Westerström. A lot of work was done. There was also the theory of convexity and faces in C-star algebra. Alveson, Efros, Sternberg were involved, but the conclusion is that, well, there is no counterexample. I think the consensus, I believe there probably is a counterexample, but it has not been found, and I will explain why it is difficult. But if you go to the local case, if you ask now whether the contractive local lifting property is true, then it is true. It is always true. So all C-star algebras have the contractive local lifting property. And so you see, I put this problem in the same collection of problems, because I can say, well, this is a problem about does local lifting implies global lifting? Because we are asking whether global lifting is always true, and we know local lifting is always true. So I think it fits. Something that's less well known is that, in fact, from this early literature in the 70s, you can see that things are exactly the same if you replace contraction by positive contraction. So it's the same. The lifting property is open, and the local lifting property is known to hold. It is true. This is from Westerström's work. So when positivity is involved, of course, I restrict the finite dimensional subspace to be a little better than just a finite dimensional subspace. And really, we will always work when positivity is involved with so-called operator systems, finite dimensional operator systems, which are defined as subspaces that contain the unit and are self-adjoint. But, well, it fits also the previous pattern just as well. But it's clear that positivity will require actually to work with such slightly less general E to get something interesting. So now an important thing that needs to be emphasized is that, and this I'll come back to that of course later, is that any separable unital C-star algebra is a quotient of a universal, very important C-star algebra for these lectures, the full C-star algebra of the free group on countably infinitely many generators. Okay, so any separable C-star algebra, it's actually a very fairly easy result, is a quotient of C-star F infinity. But now, once we know this, it turns out that it suffices to consider the lifting property for homomorphisms. So if we have, sorry, no, I'm yeah. So we'll have the F lifting property, which actually, this is what this equivalent definition is trying to emphasize. The F lifting property can be restricted to the case of unital star homomorphism. So I was fuzzy about F. So the class F will be, script F will be such that at the minimum that it must contain is all unital star homomorphisms. And what this definition is saying is that if we can lift the unital star homomorphisms, then we'll be able to lift everything. Okay, so the problem will be about for our lifting problem. That's for our problem number one. The problem reduces to this situation. Okay. Now, a related comment that needs to be made, which was partially made in relation to Sobchik's theorem, is that if you have a lifting, okay, if you have a lifting and Q is lifting R and Q is the quotient map, then the composition of Q, the composition QR is going to be the identity, of course, of the quotient, but RQ, now RQ is a map on C, which is, it's immediate to see, it's a projection, and the complementary projection, identity of C minus RQ, is a projection onto I. So we have, if we have a bounded lifting, it's immediate that we have a bounded linear projection onto the ideal. But the norm will be bounded by 1 plus the norm of the lifting. So if the lifting has norm 1, we get a projection of norm 2. And we get that our algebra as Banach space is decomposed as a direct sum in the Banach space sense of I with this complementary subspace RQ of C. So the problem number one, if you are not insisting on the fact that you want a lifting to be contractive, you know, you're allowing yourself to just have a bounded lifting, it is actually still open in this generality, and it can be phrased simply as saying that, is it true that every ideal in a separable C-star algebra is complemented? And the amazing thing is that, you know, after 50 years of operator algebra theory, this is still open. I find this, frankly, very shocking, and I have deliberately tried to emphasize that this problem is open because I think this is important. Now, this will perhaps come back at a further remark later, but maybe I can insert here that the theory has a certain more abstract theory of M ideals has been developed, which is modeled on what happens for ideals in C-star algebras. And in the theory of M ideals, the corresponding problems have been solved by a counterexample. But it is not known for ideals in C-star algebras that there is a counterexample for our problem one. Let me say now, let me come to a very beautiful theorem, which is due to Arveson, which I try to develop again in this slightly abstract way, because that's need, you know, in the sequel. So the principle, I call it Arveson's principle. The principle is simply, can be stated just very simply as this first line here. It's a little bit surprising if you think of it. Pointwise limits of liftable maps are liftable. And you would think that pointwise limits of, you know, maps that are good, well, in this setting, you know, of course, norm limits, you understand, norm limits, uniform norm limits will be liftable. But for pointwise limits, there's a subtlety here, which is related to the existence of these quasi-central approximate units. Okay, so there's a condition on the class F that I need to put in addition to the one I've already mentioned, and it's a certain non-commutative operator theoretic convexity. And the class F now is required to satisfy this. Whenever we have a positive element in norm less than 1, we want that if we mix two maps in F, little f and little g, and we combine them by this expression using sigma, and you should think of this as a generalized convex hull, then you still get a map that belongs to F, okay? So of course this implies that F is convex because you could use just a scalar in place of sigma that gives you convexity, ordinary convexity. So now, what does the principle say very precisely? Well, we have the set of liftable maps, F liftable maps. The set of F liftable maps is just the set of maps that can be written as Q composed with a map in F, okay? So this is what I will just denote Q script F, Q of F like that. And the theorem says that when E is separable, so I think this E here should have been X, that's a misprint, this E probably is X in this discussion. So then the pointwise closure, the closure for pointwise convergence of QF is equal to QF. I guess I'm assuming that here the class is pointwise closed.
Professor, old, very
yes.
Old. Very, he's here now again.
Is there a question?
Some of, I don't know, students or. Yeah.
Shall I continue?
Yeah, I mean, Vistas, can you mute yourself?
It's for department, yes. It's kitchen, so it's public. That's the bad part.
Hello.
Yeah, very loud. Very loud.
Is there a problem with the picture or the sound?
No, it's going on. So only one participant unmuted himself. Please,
okay.
Continue.
Okay. So a simple illustration of the consequence, just to show you that even very basic facts are included in this statement. So if the principle of Arveson in particular tells you that if you can find liftings of norm less than 1 plus epsilon for any epsilon given in advance, then you can find a contractive lifting. I'm pointing this to show that this is not obvious, because your obvious, reaction to this will be, oh, okay, if we have this net, then I'll go to, some weak star limit or weak limit, but you can do this, but a priori, this brings you to the bidual if you take a weak limit. So the statement is that this works for pointwise norm convergence. And so here it's obvious that this is a particular case. It tells you there will be a contractive lifting. Simply because this line, because the maps, the map U in this case is obviously a pointwise limit of maps that are liftable. This map will be, this map divided by 1 plus epsilon is liftable by a contraction, and it tends pointwise to U. So that gives us the result. Okay, that's part of the principle. And another even more classical fact, which is of course related to this, is that when you take the unit ball of a quotient C-star algebra, an element in the unit ball can always be lifted by an element in the unit ball of C. And as you know, for quotient Banach spaces, usually you need to lose an epsilon when you lift. You only have that the open ball is mapped onto the open ball. Here, the closed ball is mapped onto the closed ball. Okay, so we will apply it to a bunch of classes F. So we can apply to contractive maps, but if we suppose, I will mostly consider the contractive case, but if we actually want to generalize, then we might apply it to maps that are not contractive, but that have a norm bounded by a fixed constant C. That works just the same. And so the same principle will work. You could say C plus epsilon gives you C also, just like the preceding remark I made. Then the class of positive contractive maps, we already mentioned it, and I will come in a moment to completely contractive, completely positive contractive maps, and unital completely positive maps, which will be, these last three classes are really our main subject. So in all these cases, the class is admissible and the principle is valid because of the existence. The key idea is a central approximate unit. I'm hearing some noises. I don't know if this is because of question or just because of white noise.
I don't think that there is any question, so please go ahead.
Okay. So here comes a very important screen to explain, the point of view that I'm taking in the lecture, because my lecture will concentrate on lifting problems, but then suddenly you're going to see me telling you about extension properties and injectivity, while I'm interested in lifting problems, which is like, projective questions. Of course, you could say that by duality there's a connection, but this is not it. It's not duality now that I'm coming to. It's a different thing. So I'm interested in the problem whether local lifting implies global lifting. So let's look at the diagram. So the diagram is here for local lifting. We have this situation. The restriction of U to E is here. And we are trying to find this map U upper E with E upper index, okay? But now suppose this is not automatic at all. Suppose that actually this map little u upper E extends to A, just so that the diagram here is commutative. I will never write a diagram, I think, or I might make a mistake, that is not commutative, okay? So when I write a diagram, it means it's commutative. So assume that we have this extension, capital U of E, and that it is still in F. So now this is an extension problem. I just looked at this map U E, and I said, oh, suppose I can extend it in F. Well, if I can extend it in F, now I get a net of map, capital U upper E, that tends pointwise to my original U, because you see on E, on any large finite dimensional subspace of A, it coincides with the original map. That's just what the diagram says. So this net of maps U of E tends to the map U. Sorry, when I compose it with Q, I forgot. Of course, Q, capital U of E, now tends pointwise to U. Okay, so this is, I'm forgetting to read my own screen. I'm just reading the diagram, which is the right thing to do, really. All is on the diagram. So QUE tends to U pointwise when, the net of subspaces tend to A. Well, Arveson's theorem tells us, okay, in that case, the map U is liftable. And so this is, of course, if and only if, because if your map was globally liftable, then you have no problem to find, your extension UE. You have a single map that globally lifts. So this is an amusing situation where you see the lifting problem becomes really an extension problem, okay? Okay, so that's what I wrote in the conclusion. The principle of Arveson shows that when we are asking ourselves to pass from local lifting to global lifting, then actually there's an extension problem that comes up. Okay, so in particular, if you're willing to make an approximation assumption on, for instance, the map U, so you assume that the map U from X to C over I that you're dealing with is approximable, So in the sense that it's a pointwise limit of finite rank maps with, say, norms uniformly bounded by C, then you will get, by the previous reasoning, you immediately will get a lifting from X to C with norm less than C. In particular, if X has the metric approximation property, then we get the lifting property for all contractive maps. So if the space X has the metric approximation property, if X is a C-star algebra, like before I called it A, if the algebra A is a C-star algebra with metric approximation property, automatically it has the lifting property as we considered it for contractions. And the proof is, of course, very clear. You have this approximation of finite rank. You have ranges of these finite rank maps, which you call EI. They are finite dimensional. And then you will be able to lift from EI to C, because you know that the contractive local lifting property holds. It is true. This is always true. This is what we started with, okay? And so you can lift by this Ri, and since you have this Ui available, the composition Ri Ui gives you maps that are liftable and tend pointwise to U. Conclusion, your map U is liftable. Okay, so you see the problem, of course, would be solved if we knew that C-star algebras all have the approximation property, or better, the metric approximation property. And this was open for a long time, and a very difficult, very deep counterexample that actually there hasn't been any other way than Shankovsky really to produce a counterexample. Shankovsky proved that B of H fails the approximation property of Grothendieck. And it implies by abstract reasoning that there are separable unital C-star algebras in B of H that fail the approximation property, but no more concrete example has been found. Only the things that can be derived trivially from B of H. So, for instance, it's still not known whether the full C-star algebra of the free groups have the approximation property. This is open. Although from famous work of Hagerup, it is known that the reduced C-star algebra, it's a very surprising fact when it came out. It came out in around, I think, late 70s, close to 1980. A little before Shankovsky, actually. Hagerup proved that the reduced C-star algebra of the free groups has the metric approximation property. The full one is open. Okay, so if one just uses a slightly generalized form of the argument that we just used, we can say formally introduce, you see where I'm heading, you can formally introduce the notion of F approximable. You just take finite rank maps in F that approximate U. And so the same reasoning says that if your quotient has the F local lifting property and the F, and if it is F approximable, so you need both F approximable and F local lifting property for the quotient, then the map U will be globally F liftable. And so again, the formal statement, if the quotient has the F approximation property and local lifting property, then the quotient itself, not the map, but the quotient has the F lifting property. Now, let's see, I guess I have, Arasa, I still have a few minutes.
Yeah.
Okay, so maybe I should take just 5 or something. Okay, so I now come to the case of biduals. The case of biduals is very important in the whole discussion, because if we pass to biduals, actually in some sense, one can say that lifting becomes very easy, almost trivial, because if you pass to biduals, then the difficulties that we've emphasized before disappear. So automatically the bidual splits as the direct sum in the C-star algebra sense. So this direct sum is direct sum of two C-star algebras, and it's, you know, how to say, block L infinity direct sum. So the norm, so the unit ball of C star star is the product of the unit balls, the two factors here. And in particular, we have an isomorphism of the bidual of the quotient and the quotient of the biduals. And so when you look at the lifting problem, our favorite lifting problem with the diagram, you see that if we enlarge the range, the quotient range C over I by passing to the bidual, then things are very easy because the quotient map, the bitranspose of the quotient map, admits a lifting. This is what is reflected, of course, by this identity, you know, in the first line. So here we have a lifting, and so we can lift our original map U to a map V, which is a good lifting, but it has one defect. Of course, it lifts only into the bidual. So it's easier, obviously, if your range is larger, if your target is larger, it's easier to lift into that target. And that's the case here for the bidual. So the concept that now enters the discussion and plays a big role is that of local reflexivity. So the local reflexivity principle in Banach space theory goes back to Lindenstrauss and Rosenthal. It's a very important fact, beautiful fact, which now has very simple proofs, but still, you know, it's, you come to, if you never met this, it's not so obvious. And it says that if X is finite dimensional, so the original space here must be finite dimensional, the Banach space of bounded operators from X to a bidual is the same as the space of bounded, as the bidual of the space of bounded operators from X to C. And this is isometrically the same. So, of course, the use of this theorem is that the unit ball of the space on the left, this is the non-trivial part, the unit ball of the space on the left is included, it coincides, but it's included, the important point is it's included in the unit ball of the space on the right. And the unit ball of the space on the right, since it is a bidual, we automatically know that it is the weak star closure of the unit ball of the original space, which is here B of XC. So in other words, the local reflexivity principle is an approximation principle. It tells us that any map from X to the bidual is nicely approximable by good maps, contractions from X to C for the pointwise weak star topology. Okay, and so I can give you as perhaps close to my conclusion here a proof why the contractive local lifting property always holds, which holds. This was, you know, in my first screens. So suppose now X is finite dimensional, we decide to call it E to fit the previous diagrams, okay? And so I do exactly what I said, that is, I enlarge to the bidual, and then I know that I have a V from E to the bidual. That gives me a lifting, but as I said, I've enlarged my target. Yes, I've enlarged my target, but now the local reflexivity principle, which I abbreviate by LR, implies that this map V is pointwise weak star, the limit of a net of contractions. This is what is expressed by local reflexivity. Okay, so if we continue, we see that we have Q star star VI tends to Q star star V, and really just chasing the diagram, obviously it gives us that actually QVI is the same as, you know, the diagram commutes, so this is the same as QVI. QVI tends to Q star star V, which is the same as U, so QVI tends to U. pointwise, so we are getting close, but only for the weak topology. So now our problem is different. The target is good, but we've lost the norm topology. We only have, the weak topology. And here, what comes to the rescue is another principle, very famous principle of functional analysis, MAZUR's theorem, that says that for a bounded convex set, weak closure and norm closures are the same. And so this principle, with just a little bit, of arrangement, tells you that if you replace your net of maps VI by convex combinations, if you replace now this map VI by convex combinations, suitable convex combinations of the VI, then you can transform weak convergence into norm convergence. So I just give you the principle, but the details are sort of fairly easy to arrange. What main point is the idea. This MAZUR theorem tells you that weak convergence can be transformed into norm convergence. Here, the convexity of the class script f is used. So I think the next screen was really saying what I said. So we get now our VI such that QVI tends to U in the weak topology, and in fact in the norm topology. So we get a new net of maps, which is in the convex hull of our original set of maps, still contractions, and now such that QVI, the new net is VI prime of x tends to U of x in norm. So now this is our map U is now a pointwise limit of liftable maps. The liftable maps are the QVI prime. So by Arveson, we have lifting whenever the domain is finite dimensional. So whenever x is finite dimensional, we have the global lifting. That's the same thing as saying that we have the local lifting. So just one last word, and then I think I can, good point to close by this screen. So if you now just have grasped the combination of the principles that are used, there is something very nice that emerges from this discussion, a very general fact, which is that when we are dealing with our lifting problem on a separable space X, and we deal with an F which is admissible, then actually the lifting property associated to F, to script F, is equivalent to a certain problem which looks like local reflexivity, but related to the space X, which is now infinite dimensional. Okay, so the space X has the F lifting property if and only if for any C-star algebra, when we look at a map in F on X with values in the bidual of C, there is a net of maps in F from X to C tending pointwise to U for the pointwise weak star topology. And now, if you just trace back the previous screens and use the argument that we've used, you will see that we get the proof of this theorem. So I think that's a pretty good point to end the first talk. The next, what comes next, is completely bounded, completely positive maps. So I will stop with this screen. Thank you very much for your attention.
We have some time to take a few questions. So any question?
I have a question.
Sure, please. More.
This lifting, will it be unique? Is it?
Yes.
Will it be unique from the local lifting to lifting? Can it, at least for some super reflexive spaces, local reflexive spaces, it could be.
Liftings. Yeah, liftings liftings usually, are not unique. And so I think uniqueness is something I haven't much thought of. I think it doesn't really enter much, but there might be cases it might be interesting to think what it means. I suspect it will mean that the situation is very restrictive. But I can't say more.
Any other questions? So one person asking what is a good reference?
Well, for that first talk, well, there are, the papers of Arveson are what I would have quoted. I take, so this slightly general viewpoint that I'm taking, I'm developing, I wrote a paper on the lifting property, which is on arXiv. I should say, I forgot to say, all my papers are on arXiv, so you can find them there. And so I would suggest go to my recent paper that has lifting property in the title on arXiv, and then look at the bibliography and then choose what is convenient for you, what is available to you. And later on, when I talk of tensor products of C-star algebras, I will advertise my last book, of course, which is devoted to the subject. So, but this is more for the other talks. I made the decision. I hope that you will appreciate it to actually stay in this first talk in a setting where I can explain everything mostly in using Banach space concepts, and still the problem is open. So we are dealing with things that are considered, could be considered hot. Hot have been hot for a long time. I don't know how to say, but been open for a long time. But I will move to completely bounded maps, operator spaces after talk 2, 3, 4, and for that my recent book is obviously the reference that I would give, and it's available online. If you do the same thing, you go to my papers on arXiv. I quote my book with the URL of the book, so the book can be downloaded from the URL. Okay.
So if there is no other questions, so let's give a big round of applause to Professor Pisier, such a fantastic talk. And yeah.
Thank you. Thank you.
Tomorrow at the same time, the continuation of the lecture will be there. So see you tomorrow, Professor Pisier.
Thank you. I have I'm that I don't see you, and I'm trying desperately to screen there, but I cannot do that. My Mac is not responding in any way.
Let's see.
Perhaps you can release me in some
bit dark here, probably.
So maybe if you stop recording, perhaps.
So is it visible now?
You stop recording.
I can see Muruganandam.
You stop recording.